Okay, talking some more about vectors with calculus. When we're dealing with vectors, we have a position vector, we have velocity vector, and we have an acceleration vector, and the relationship between position, velocity, and acceleration is the same thing that's been happening all year with us. The position vector is known as vector r, and it's made up of x of t, comma y of t, which really is parametric equations. And so when we've been dealing with parametric equations all year long, we've been actually dealing with vectors. The velocity vector is the derivative of the position vector, dx dt, comma dy dt. And so if we're doing the slope of the original curve made up by the position vector, the parametric equations, then the slope is dy dt over dx dt, coming from the velocity vector, which is dy dx. And so slope of the tangent line is working just like it has been all year long with that. Speed of the curve is the absolute value of the velocity, just like we've been doing all year long. Of course, when we have vectors, absolute value of a vector is the magnitude of that vector. So speed is the magnitude of the velocity vector. Now, one thing that we definitely want to understand is the fact that speed is not a vector. This is just a magnitude. So it's just a numerical value, non-negative numerical value. We've got the acceleration vector, which is the second derivative of the position function, or the first derivative of the velocity. And obviously you can do magnitude of the acceleration vector. Okay, so if we have a curve and you've got your position function, okay, so your velocity is the velocity vector is tangent to the curve. It's the instantaneous tangent to the curve any point along the way, and it always points along the path of motion. Okay, particle moves in the coordinate plane such that at any time t, it's some parametric equations. Find a single path. Find a single equation for its path. We've been doing this all year long. We're really just converting the parametric equations to rectangular or Cartesian coordinates. I'm seeing sine and cosine, so I'm thinking of the fact that sine squared of an angle plus cosine squared of an angle is equal to 1. And so x over 3 equals cosine t, so square both sides. Similarly for the sine, y over 2 equals sine t, square both sides. And so we can get x squared over 9 plus y squared over 4 equals 1. Now, the only thing to be careful of is just to make sure that we don't need any restrictions for this equation. We encountered that earlier in the semester. But if we plug in some points, we can see that we're getting 3, 0, and 0, 2, and negative 3, 0, and 0, negative 2, and it just is going around like that. It's the full ellipse. And so that matches up. Okay, 1b, find the velocity and acceleration vectors. Well, here's our position vector, 3 cosine t, comma 2 sine t. And the derivative of my position vector is my velocity vector. And so 3 times the derivative of cosine is negative sine t, so negative 3 sine t. And sorry, that should be in blue. So negative 3 sine t, and the derivative of 2 sine t is 2 cosine t. Okay, and acceleration vector is the derivative of the velocity vector, and so negative 3 sine t, so negative 3 times cosine t and it didn't change colors. Well, okay, and the derivative of 2 cosine t would be 2 times negative sine t, or negative 2 sine t. Okay, so there are the velocity and acceleration vectors. Okay, show that the acceleration is negative 1 times the position vector for every t. Okay, well, I can see that the acceleration is negative 3 cosine t, negative 2 sine t. And so they're both negative, so we could either factor out a scalar value of negative 1. I think that would probably be kind of nice, so let's just factor out the negative 1. And cosine, sorry. Cosine t, comma 2 sine t, which that happens to be the position vector. We can see comparing it up there, which is negative 1 times the position vector, and so we just showed that. Okay, find the position vector, velocity vector, and acceleration vector evaluated at t equals pi over 6. Okay, so cosine pi over 6 is root 3 over 2. And sine of pi over 6 is 1/2. And so that would be 3 root 3 over 2, comma 1. Okay. Negative 3 negative 3 times 1/2, 2 times root 3 over 2, which is negative 3/2, comma root 3. And finally, we have negative 3 times root 3 over 2, comma negative 2 times 1/2, which is negative 3 root 3 over 2, comma negative 1. Okay, find the speed of the particle and the magnitude of its acceleration at t equals pi over 6 and t equals pi. Well, the velocity is, the absolute value of the velocity is the speed, and so the dx dt is negative 3 sine t squared plus the dy dt. The dy dt is 2 cosine t squared, and so that would be, in general, 9 sine squared t plus 4 cosine squared t. So that's the speed of the particle at any time t for this equation. Now the speed at t equals pi over 6 then would be square root 9. Okay, sine of pi over 6 is 1/2 squared. And then I have 4, and cosine of pi over 6 is root 3 over 2 and squared. And so this is 9 times 1/4, which is 9/4. And this is 4 times 3/4, which I know is just 3, but this one's a fraction, so I think I'll say it's 12/4, which is root 21 over root 4, which is root 21 over 2. And again, this is speed. Notice that it's not a vector. It is just a numerical value. Okay, and I'm going to pause and allow you to do the speed at t equals pi. Okay, picking up where we left off, if you did the speed at t equals pi, you should have gotten that it was the square root of 4, which is 2. Okay, go ahead and double check that. But let's see. Let's go ahead and do the acceleration, the magnitude of the acceleration. Which we know is going to be the square root of -3 cosine t squared and -2 sine t squared. So 9 cosine squared t plus 4 sine squared t. Okay, that's what we're doing. And if we do the magnitude of the acceleration at t equals pi over 6, then you should go ahead and get root 31 over 2. You go ahead and double check that. Let's work through the other one, the magnitude of the acceleration at t equals pi. So that's going to be the square root. Okay, so we got cosine of pi is -1, so 9 times -1 squared plus, and then we have sine of pi, which is 0 squared, so we get square root of 9, which is 3. Okay. On the time interval between 0 and 2 pi, when is the speed of the particle a minimum? When is it a maximum? Well, let's remind ourselves what our speed was in general. So our speed in general, here it is 9 sine squared plus 4 cosine squared t. So sine squared t plus 4 cosine squared t. Now, typically when we're doing max-min, we need to do the derivative and set it equal to 0 and all that kind of stuff. But let's try to get it so it's just either just sines or just cosines. And so we can do that by doing a substitution for either sine squared or cosine squared. I think I'm going to do a substitution for cosine squared. So I've got 9 sine squared t plus 4 times, now cosine squared is 1 minus sine squared. And so if we combine, if I distribute the 4 and combine like terms, we get the square root of, I get 9 sine squared t minus 4 sine squared t, which is 5 sine squared t plus 4. Okay, so that's the speed. Now if we take a look at that, we will get minimum value well, let's do maximum actually. Max value when sine squared t is a max. Well, what's the biggest sine t ever gets? Sine t, the biggest sine t ever gets is 1. Of course, even if it's a negative 1, and then we're going to square it. So sine squared t equals 1 is when we get the max, and so that happens at, we get sine t is equal to 1 at t equals pi over 2, and we get sine t is equal to negative 1 at 3 pi over 2. So here's when we're getting our maximum value. On the other hand, we will be getting our minimum value when sine squared t is 0, or in other words, when sine t equals 0. And sine of t is equal to 0 at t equals 0 and pi. Since it's a periodic function, this would keep on going if we didn't have the boundaries between 0 and 2 pi. But anyway, there's that. Okay, moving on. Particle moves along the parabola y equals x squared minus x with constant speed, root 10. Find the velocity vector when the particle is at the point 2, 2. Okay? A lot of stuff going on here. First thing that's kind of jumping out at me is about the constant speed. And we know that speed is the magnitude of the velocity, and the magnitude of the velocity is dx dt squared plus dy dt squared, and that's going to equal root 10. Of course, if we square both sides, we get dx dt quantity squared plus dy dt quantity squared equals 10. Okay, and we need to stop and pause right there for just a bit. I also notice that we have the y equals x squared minus x, which we're able to take the derivative of both sides with respect to t. So dy dt is equal to 2x dx dt minus dx dt, GCF of dx dt there on the other side. So dy dt is equal to dx dt times 2x minus 1. Okay, and so if we substitute this over here, we can get dx dt quantity squared plus, okay, now dy dt is dx dt times the 2x minus 1, and then I have to square it. So dx dt times 2x minus 1 squared equals 10. And so if I do that, I get, I have a GCF of dx dt quantity squared here. So dx dt quantity squared, and I'd be factoring that out as a GCF, and there's left behind a 1 plus 2x minus 1 quantity squared, and that's equal to 10. Okay, now what have I not used? Find the velocity vector when the particle is at the point 2, 2. So using at the point 2, 2, I can plug in 2 for x and a 2 for y at that point. So I've got dx dt quantity squared times 1 plus, okay, now 2 times x is 2, so 2 times 2 is 4. 4 minus 1 is 3. So the inside there is 10. If I divide both sides by 10, I get dx dt quantity squared equals 1, which tells me that dx dt is equal to either plus or minus 1. And remember, we're going for the velocity vector, and so the velocity vector is made up of dx dt comma dy dt. So we're going to take advantage of that. Now we had what dy dt was equal to, so we need to continue on with that. Okay, so dy dt is equal to dx dt, which we know is either plus or minus 1 at the point 2, 2. So plus or minus 1 times 2 times 2 minus 1. So dy dt is equal to plus or minus 1 times 3, so dy dt is equal to plus or minus 3. And our velocity vector is made up of dx dt comma dy dt. And so using all of that together, our velocity vector then is plus or minus 1, comma, plus or minus 3. Okay, now we could go ahead and take a look at it visually. We had the parabola, y equals x squared minus x GCF of x. So y-intercepts of 0 and 1. And it's opening up so just a quick little sketch. It should be going through the point 2, comma 2, and I'm still getting used to this thing. But 2, comma 2 is presumably about right here. And so if you take a look at your vectors, the positive 1, positive 3 would be doing essentially something like that. And the negative 1, negative 3 would be doing something about like that. They're just opposite vectors. If the motion of a particle on the x-axis has acceleration and it is stationary at x equals 1 when t equals 1, then 12 times x of t is equal to. Okay, so well, if we integrate second derivative of x with respect to time, and we'll integrate that with respect to t. Of course, we get dx dt, and I get 1/3 t cubed minus t squared plus a constant. Don't forget plus c. Okay, now it's stationary at x equals 1 when t equals 1. So stationary, that's telling me that dx dt equals 0 when x equals 1 and t equals 1. So 0 equals 1/3 times 1 cubed minus 1 squared plus c. So c is 2/3. Okay, and so now we plug that in. So we've got dx dt equals 1/3 t cubed minus t squared plus 2/3. And we are going to integrate that with respect to time. So now you could have done the separation of variables here and just have the dx and then move the dt over, or this is also acceptable where you have that dt right there. Okay, so integrating 1 with respect to x, so I get x plus a constant, but we move that to the other side. And I have 1/3 times 1/4 t to the 4th, so 1/12 t to the 4th minus 1/3 t cubed plus 2/3 t plus a constant. Okay, so coming back to this, stationary, we don't have the stationary anymore, but we have x equals 1 when t equals 1. And so 1 equals 1/12 minus 1/3 plus 2/3 plus c. Okay, so looks like common denominator is going to be 12. So I've got 12/12 minus 1/12. Of course, minus 1/3 plus 2/3 is positive 1/3, so subtract minus 1/3, and 1/3 is 4/12. So minus 4/12 is C. And so 12/12 minus 4/12 is 7/12. Okay. And so if I plug that back in right there, and so I've got x of t, x equals 1/12 t to the 4th minus 1/3 t to the 3rd plus 2/3 t plus c. Sorry, c, we already figured that out. So 7/12. But we're supposed to be finding 12 times x of t, so if we do 12 times that, basically all the fractions are going to go away. So we get 12 times x of t is equal to t to the 4th minus 4t to the 3rd plus 8t plus 7, which is choice B. Okay, moving on. Particle moves in the plane according to the parametric equations. Remember, parametric equations are just vectors. Each of the following vectors is orthogonal. Okay, orthogonal. That's parametric. Sorry, not parametric. That is perpendicular in a three-dimensional sense. To the acceleration vector. Okay, so the perpendicular to the acceleration vector at t equals pi. Okay, so that means we need the second derivative of x with respect to time and the second derivative of y with respect to time. Okay, so dx dt product rule, t times negative sine t plus cosine t times 1. Okay, and the second derivative of x with respect to time. Product rule here again, so I've got first times derivative of negative sine t is negative cosine t plus the second, which is negative sine t, times the derivative of the first, which is 1, plus the derivative of cosine t, which is negative sine t. Okay, and we're evaluating that at t equals pi. So I've got pi times, okay, Okay, cosine of pi is -1. Opposite of -1 is +1. Sine of pi is 0, -0, that's still 0. So pi. Okay, and I also need second derivative of y with respect to x. So second derivative of y with respect to t. So dy dt, product rule again. So first times the derivative of the second plus the second times the derivative of the first, which is 1. And the second derivative of y with respect to t, first times the derivative of the second, which is negative sine t, plus the second times the derivative of the first, which is 1. And the derivative of sine t is cosine t. Okay, so evaluating that at t equals pi would be pi, and sine of pi is 0, cosine pi is -1, and cosine pi is -1, so -2. Okay, so my acceleration vector at pi is pi, comma, -2, but that's not what they're asking for. They are asking for orthogonal so we want perpendicular to that. Now, acceleration, this is really a delta x and a delta y. So the slope is -2 over pi. So if I want perpendicular, opposite and reciprocal, so I'm going to have 2 and a pi. Not that. And this slope was negative over here for the acceleration, which means I want this slope to be positive. And so 2 comma pi would be a possibility. It could be plus or minus, as long as they're both positive or both negative, it would work either way. And so which one is giving me that? And that is going to be C. Okay. Find the vector that is opposite in direction to the velocity vector at t equals 4. Okay, so, well, let's figure out what the velocity vector is. So if this is x and y, so we need dx, dt, and dy, dt. So dx, dt, I could just bring the 1/4 out in front, so 1/4 and 3t squared minus 4t. And if I evaluate that at t equals 4, we get 1/4 times 3 times 16, 48, minus 16. So 1/4 of 32, which is 8. Okay, dy dt. How do I press this? Dy dt is equal to 2t minus 1 evaluated at t equals 4, which is 8 minus 1, which is 7. Okay, so if we put that together, the velocity vector at t equals 4 is 8, 7. Now that's not what they're asking for. They said find the vector that is opposite in direction to the velocity vector. Okay. So by the way, it's obviously not d. Now opposite in direction is just -1 times the vector. So -1 times velocity vector would be -8, -7, and that is there. Now the direction of the vector could be written as a unit vector or unit vector, which presumably the length of the vector is √113, so it could be written like this, -8 over √113, -7 over √113. But that's not how they have it written. They don't have it written like that, so it is choice E. Okay. Again, parametric equations, acceleration vector at t equals 2. So you need the second derivative of x with respect to time and the second derivative of y with respect to time and evaluate at t equals 2. I'm going to let you go ahead and do that one. I will go ahead and let you know that A is the correct answer, but I'm going to let you do that problem. Okay. Find the unit vector tangent to the curve, parametric equation, x of t, y of t, at the point 4, 7. Okay, so a vector that's tangent to the curve is the velocity vector. Okay, so we need dx dt, dy dt. So dx dt is 2t, and dy dt is 3t squared. Now, all the others up above, we had it at the point, we had it at t equals something, and this one is at the point. Okay, well, first off, this is an x and a y, and I have x and y stuff going on here, so let's see if we can figure out what time that's happening. So x is 4, so 4 equals t squared, so that would be t equals plus or minus 2. not necessarily just positive, so we can't just assume that. Let's check the y. So 7 equals t cubed minus 1. So 8 is t cubed, and so t is just 2. And so t equals 2 is when that is happening. Okay, so evaluating at t equals 2, we get 4, comma, 12. That's our velocity vector. But they said find the unit velocity vector, find the unit, the unit vector tangent. So it's not a unit vector right now. So if we do the magnitude of that, we get 16 plus 144 root 160, which is 4 root 10. And using this, we've got 4 over 4 root 10, comma, 12 over 4 root 10, which reduces to 1 over root 10, comma, 3 over root 10. Which I see that as choice C. Okay. Technically, it could be plus or minus, as long as the pluses match up and the minuses match up. Now, 7b, find the unit vector normal. Now remember, normal means that we're doing perpendicular to the curve. And so this is tangent to the curve right here, the one that we just did before. And so if we're doing perpendicular, we need to have the 3 root 10 and the 1 over root 10 trade places. Opposite and reciprocal. That gets us our reciprocal. The opposite, now this one was going to be a positive slope no matter which way we did it. So the one down here we need it to be negative. So this one could be plus or minus, but this one over here would be minus plus. So the plus matches up with the minus. Okay, now it could show up either way. And if we look, looks like B matches up to that.